gonna try recording this for upstairs. Anyway, I want to start our engineering unit by showing you about Galloping Gertie, which is the Tacoma Narrows Bridge. And it was built in 1940, or it opened in 1940, and at that point there was a push to try to make slimmer, more elegant looking types of bridges. And so the original design that was submitted was rejected and they redesigned it. And when the bridge opened, they found that it had some issues, and it did get the nickname of Galloping Gertie. Eventually they rebuilt the bridge, and now it's called Sturdy Gertie. But let's see, let's watch the story behind Galloping Gertie here.
Beautiful, light, and flexible, the Tacoma Narrows Bridge was built like no other suspension bridge. It was unique in its design and incredible in its appearance. But on November 7th, 1940, it all came crashing down. The collapse was one of the great tragedies in engineering history. Never had a suspension bridge so important met its end so catastrophically. But the Tacoma Narrows Bridge's true legacy was not in the frantic headlines generated by its collapse, but in the revolutionary changes it brought to the world of engineering and bridge architecture. That was Galloping Gertie's triumph. In the 1920s, America was prospering and optimistic. Skyscrapers and bridges were seen as symbols of elegance and power. Then, with the 1930s depression, cheaper and more efficient bridges were needed. As a result, bridges were made as simple as possible, graceful and slender works of art, beginning a trend towards light, flexible bridges. The Tacoma Narrows Bridge was proposed to connect the Olympic Peninsula and the Washington mainland. The Washington State Department of Transportation appointed Clark Eldridge to design the bridge. Eldridge's plan was examined by an out-of-state engineering consultant, the world-famous suspension bridge designer, Leon Mosef. Mosef suggested replacing the 25-foot deep stiffening truss with an 8-foot shallow plate girder. Conforming to the trend, this lessened the cost of the bridge and gave it a slender, artistic appearance. In 1939, construction of the $6 million bridge began. On July 1st, 1940, the Tacoma Narrows Bridge officially opened. It was the third longest suspension bridge in the world. Thousands of people attended the ceremonies. Thousands more worldwide were intrigued by the bridge's extraordinary width-to-length ratio and its exceptional flexibility. But the Tacoma Narrows Bridge had an even more fascinating characteristic: its bounce. Engineers were puzzled by these strange oscillations, but they did not doubt the bridge's safety. In fact, the bridge's movement attracted thousands of people who crossed the bridge just for the exhilarating experience of watching the car in front of them disappear. For this, the Tacoma Narrows Bridge was quickly nicknamed Galloping Gertie. Galloping Gertie proved to have many more benefits. It linked the less developed peninsula to the industrial Tacoma area. There was rapid land development and population increase. The bridge also benefited the military, connecting the McCord Airfield and Puget Sound Navy shipyard. All around, the bridge was a marvelous success, but Gertie began to run into problems. The engineers grew more worried about the bounce. Leon Mosef was contacted, but he assured them that it was not a problem. The engineers hired Professor F. Bert Farquharson at the University of Washington to build a scale model of the bridge and test it, while also studying the real bridge. We knew from the night of the day the bridge opened that something was wrong. On that night, the bridge began to gallop. Attempts were made to control the motion by installing hydraulic jacks and tie-down cables, but these proved ineffective. Farquharson observed a torsional twisting in the bridge model, different from the regular bounce. He recommended adding wind deflection devices, and preparations were made to install them, but the bridge did not meet nature's deadline. On the morning of Thursday, November 7, 1940, winds whistled across the Narrows. The bridge was rolling 2 to 5 feet. Suddenly, the bridge went into a lateral twisting motion. The sides rose and fell 28 feet up and down every 5 seconds, tilting at a 45-degree angle. Leonard Coatsworth was on the bridge when it began its violent twisting. He got out of his car and fled the bridge. His dog Tubby was left in the car. Car Carson arrived to record the event. The bridge had been closed by officials alarmed by the dangerous motion. Observers were worried, but very few expected what would come next. The first section of concrete from the center span broke off. The bridge began a violent motion. Steel girders twisted, cables snapped, lampposts broke off, and pieces of concrete fell. Then, 2 minutes later, a 600-foot portion of the center span plunged into the Narrows.
What's you mean? How's he just forget his dog? It doesn't make sense.
Howard Clifford, a newspaper photographer, was one of the last people on the bridge.
It was bouncing so that it would go up where I was, and then it would snap down so fast, and I would go that drop as fast as that went down. I would be going down. This was coming back up, and it hit me every time and knocked me down.
Along with pieces of the deck, Leonard Coatsworth's car and dog fell. The dog was the only casualty of the collapse. 11:10 a.m. saw the end of it all. Galloping Gertie hung limp and broken. The hopes it had inspired had been crushed. The tragedy was complete. Gertie's collapse came as a shock to the public. Many people were angered, blaming it on faulty engineering. They felt that their tax money had been wasted, and more would be squandered for conducting studies and rebuilding.
Nobody thought it would go down, no. I mean, if they thought it was going to go down, they would have closed it right away and tried to figure out what to do.
Several committees were appointed to analyze the cause of the collapse. The Federal Works Administration set up a group of professional engineers. In March of 1941, they announced their findings in a report. Part of the problem was that the solid plate girders on the side caught the wind like sails. The original truss design would have allowed the wind to pass through harmlessly. Also, due to its exceptional width-to-length ratio, the bridge was extremely flexible and fragile. Still, the winds had not been overly powerful. In fact, they scarcely exceeded 42 miles per hour. So what did prompt it? As the wind passed over and under the bridge, it created vortex shedding, where wind eddies formed on the opposite side. These eddies gave small pushes to the structure. Although the force wasn't especially great, the vortices caused the bridge to sway rhythmically. Eventually its motion became self-excited, meaning that it propelled itself. The bridge's drastic motion was caused by harmonic resonance. The basic idea is that everything vibrates at a natural frequency, which can be approached by outside forces. This concept is illustrated by a mathematical theory later suggested by Theodor von Karman. On that day, the frequency of the wind was close to the bridge's natural frequency. This resulted in a very small denominator, which made the amplitude of the motion huge. Unfortunately, such science and mathematics were overlooked at the bridge's construction. Galloping Gertie's collapse drew attention to them, and it continues to be a challenging puzzle for engineers all over the world to study and learn.
So basically, what happened is, so you guys, I think in 7th grade you learned that all matter has particles in it, right? And when you're talking about a solid or a liquid or a gas, you know that those particles vibrate at different speeds. So a solid, the particles are really close together and they kind of just jiggle right next to each other, and then you add some heat, and in a liquid they start to move a little faster, and then in a gas they're moving all over the place. So what happened here is that as the wind made the bridge move, it started to get in line with the vibration, the natural vibration of the particles that were in that material. And so when she says it basically excited itself, so when it got to the right frequency where these particles were already jiggling, it like made it jiggle faster because it got excited. It was all, yay, I can move really fast now. And so like it basically, the wind started it, but it got to a point where the material that it was made of jiggled at the same rate that the wind was making it jiggle, and it made it jiggle like twice as fast. So the particles inside the matter became excited, almost like a liquid, like it would if it had been heated to a liquid. So instead of moving like a solid, it started to move more like a liquid, which cement and steel and stuff like that should not do, okay? So basically when she's talking about like harmonic frequencies, that's sort of what's going on, is that jiggling gets amplified because it's already jiggling. Everything jiggles. We learned that, okay? In 7th grade, we learned that everything has particles inside of it, and those particles are always moving, all right? And so it got to the point where it was jiggling twice as fast as it should. And so it started really moving. So that's what happened that day. It was a little bit windier than normal, and the wind made the waves that were coming through made the material start to jiggle even more. And yeah, the guy, I guess he left his dog, or it looked like the dog was on the bridge. Maybe the dog just wouldn't come. Did you see it? It looked like it was on the bridge, maybe just sort of sitting there. This other guy that they interviewed said that as you would walk across the bridge, one part's coming up and you're still sort of coming down from the last oscillation, and that would make it really hard. Think about, trying to think, like a trampoline or something. Like if you're on a trampoline and somebody's jumping and you're just trying to walk across the trampoline, it can be kind of difficult, right? Your legs feel like you need to bend them, and well, that's sort of how it would have been to walk across this bridge. It would have been like somebody jumping on a trampoline and you're just trying to walk across the trampoline. It would have been very hard to do. And so maybe the dog was just scared. It wouldn't come. But the guy didn't, he didn't risk his own life running out for it. And honestly, I can't say I blame him, I mean, if it was my kid, maybe, but I don't know. I don't have dogs.
Just bring it with you in the first place.
Yeah, I know.
Yeah, like when you first get out of the car, just grab your dog and run.
You're right. The dog did look small. You're right. But, if that's all you took away from this video so far, shame on you. All right, let's watch the end of the video real quick here then, and it's just a couple more minutes long here.
When Galloping Gertie collapsed, hopeful newspapers speculated that it might be rebuilt within the year. Then, World War II struck, and Gertie's remains were seen as a valuable mass of steel, and the state paid workers to salvage the material. Meanwhile, Farquharson had conducted groundbreaking studies on the model bridge, greatly advancing wind tunnel testing. British engineer W. Austin came to study the Second Narrows Bridge to help plan an English suspension bridge. Quote, "The whole of bridge engineering has profited by the fall of the Narrows Bridge. The subsequent research at the University of Washington is one of the most significant steps in bridge design in many, many
Basically,
years."
they're saying that
Indeed,
it was a good
the
thing.
Tacoma Narrows Bridge was followed by the Mackinac Strait Bridge and the Verrazano Narrows Bridge, both benefiting directly from the lessons it taught. Before launching plans for a second bridge, it was decided that the solution to offer least wind resistance was an open stiffening truss. No expense was spared in building the second Tacoma Narrows Bridge. The bridge had 33-foot stiffening trusses, wind grates, and hydraulic shock absorbers. It was the most technologically advanced bridge of the time, and the years of research in aerodynamics and mathematics triumphed in enriching the science of bridge engineering all over the
Notice
world.
how much
A
wider it
writer
is.
called the second Tacoma Narrows Bridge epoch-making.
First one was like
Galloping
that.
Gertie's sequel, fondly nicknamed Sturdy Gertie, set the standards for modern bridge design, terminating the trend of lighter, flimsier bridges. Wind tunnel testing is now mandatory for all suspension bridges. The second Tacoma Narrows Bridge picked up where its predecessor had left off. The tragedy of Galloping Gertie's collapse led to triumph, revolutionizing science and architecture, directing the change from light, flexible bridges to strong and dependable bridges, and bringing a wealth of new knowledge to the engineering world. And although an unprecedented initial success resulted in tragic failure, the Tacoma Narrows Bridge rose to triumph in the end. Stable, safe, and still beautiful, Sturdy Gertie remains as a lasting testament, power achieved by grace and artistry, and a triumph that has shaken itself out of the ashes of tragedy.
So that that video helped us to understand some of the advances that were made because of the bridge collapse. It is a sad story, but luckily only one life was taken, the dog. I mean, luckily, because there have been bridge collapses that have taken lives, many lives. When I was, I want to say sometime around, maybe it was July of 2007 or June of 2007. I can't quite remember exactly, but I think it was that year. We had a wedding out in Minneapolis, and there's a bridge out there, and we went across it several times that week when we were out there for a friend's wedding, and like the following week it collapsed, and I think 13 people died. So like bridges collapse, and we have a lot of bridges here in the Pittsburgh area. It's something like in the metropolitan area of Pittsburgh, we have something like 1,700 bridges. And the only metropolitan area in the world that has as many bridges as we do, or more than we do, is Venice. And if you know anything about Venice, Italy, it's underwater. So it should have a lot of bridges. But Pittsburgh's got quite a few. And it was not until the bridge collapsed in Minneapolis in 2007 that the whole country started going crazy. Let's check our bridges, because after a while, bridges do wear out because, they have a strain on them every day. They have to deal with the weather. As you saw with Galloping Gertie, the wind ultimately was its downfall. And you just take that for granted that you're driving over these bridges every day and that they're safe. But after the Minneapolis bridge collapse, the United States, they sent out inspectors and they inspected bridges, and there's a lot of bridges in Pittsburgh that were shut down after that. And most of our bridges at the time received out of a B, C, D, and F scale. Most of our bridges were deemed to be a D or lower. Not good. And that's why in the last 8 or 9 years, there have been many bridges that they've started to rebuild and redo. And that's part of the reason why, because every so often, bridges need to be updated, or they will eventually break down from the strain. And we certainly don't want that to happen when there's when it's full of cars and things. And when engineers design a bridge, they have to design it to think about what is the biggest load that could be on this bridge at any one time. It could be filled with, let's say, Mack trucks at rush hour, and there's an accident at the end of the bridge, and everybody has to sit there for like 2 hours. And they have to design it with that in mind so that it doesn't fall down. Now, Galloping Gertie, you saw, was originally designed to have a truss system underneath the deck. And it was supposed to be, I can't remember how many feet they said, 20 feet or something like that. It was supposedly more significant than what it ended up being. But basically, they were going to put a truss system underneath. So the suspension cables would hold it up, but then the truss system underneath, and if you guys know anything about geometry, you know that the strongest shape is a triangle. So basically, a truss bridge takes advantage of triangles, and it's full of triangles underneath there. So it makes the deck a lot sturdier. And then you use the cables, the suspension cables, basically to hold the bridge up. But when at this time in history, they were trying to design more elegant and pretty bridges, which it's nice to have an elegant and pretty bridge. But if you're taking this, and they said the final underneath the deck was something like 8 feet, so it was like this, that's a significant reduction. And even if they put trusses under there, it looked like though it was solid, because they said that the wind couldn't get through it, and the wind then was creating these little eddies as it went over and below it, and started to make the bridge which the bridge was flexible, and that can be a good thing because sometimes flexibility means that it has less of a chance of breaking. But once you get from, maybe it's bouncing up and down a little bit, and then all of a sudden it starts to twist, and it's just not going to be able to take that. And you could see it started to twist at something like 10 a.m. and by 11:07 or something, it fell down. So it only could take that strain for a little while. All right. So we're going to start our engineering unit here. And lesson 1 is all about the design process. Now, for those of you that are in C-Perch, you have learned a lot about the design process. And one of the key things in the design process is design it, build it, test it, redesign it. Right? Go back, think again, because it didn't work right the first time. And Galloping Gertie, while it was not very successful as a bridge, it was very successful in helping bridge design process. They went back to the drawing board and had to redesign it. That guy went in and he built a full-scale model in a wind tunnel, and even before it collapsed, he said, "Man, this thing's gonna go." He saw that movement. You saw the video of it. He saw that movement in his wind tunnel and said, "This bridge is not gonna last." And they were planning to try to adapt some sort of a wind device on it to keep the wind from doing that to the bridge. They just didn't get it done in time, unfortunately. Thanks. All right, how do I?
Oh no.
My computer doesn't want to go forward. Go forward, please. Go forward. All right. Does anybody see any other way for me to forward this besides right here?
Can't you scroll it down? You just scroll
Oh,
down.
scroll it. Yeah, you're right. Scroll it. No, it doesn't scroll.
Can you drag it on the side?
Oh, yeah. See, this is when 8th graders are smarter than their teachers.
Yeah.
No. Try again. Try again.
Isn't there like a down arrow on our?
Oh, there it goes.
There you go.
Yeah, the down arrow. I was trying to use the down arrow before and it wasn't working. All right, there we go. So you guys have a sheet in front of you that you're going to want to keep. You can put it in the folder that I gave you guys with the foldables. All right. So in lesson 1, it says technology breaks barriers. So we need to know what is technology. When you guys think of technology, I think you're mainly thinking of technology as like computers and iPads and phones. But no, technology can be more than that. All right? Technology is the application of science for practical purposes. It doesn't have to be something that is expensive or fancy or like cell phone, computer processor type things. No. It can be products, processes, systems, all right? Any of those things are technology. I would like to just point out to you, and I apologize in the video. Hello, video people. So anybody that's not here like Sabrina can watch us on the video, but you're going to have to get the notes on Schoology, which I'll post those later on Schoology, because they're backwards in the video, because I'm using the mirror image. I want to see myself as I videotape myself. Woo! All right. You got yourself in one of my videos. I want to hear it.
Yeah.
Yeah. All right. So the method used to develop new technology, we call that the engineering design process. Okay? So if you have an idea for a technology, even like this pen, okay? Think about when, like if I go back, I'm not even sure how long ago I have to go back, 200 years maybe? I don't think that they had ballpoint pens 200 years ago. I'm not sure though if they were using a feather in an ink pot 200 years ago. They might have been using a pen that you had to dip in an ink pot and then write, so like it didn't have ink in it. But go back further, they would have, at some point they used a quill, which is basically a feather sharpened to a point. They would dip it in the ink and they would write. It was pretty messy. I mean, I'm sure you can imagine how messy that could be, right? But a pen, you know, like this is it comes apart. There's this little thing inside. It's got ink in the tube. And then it comes down this little metal tube. And at the very end, there's this little roller ball inside there, which allows some of the ink to escape. Put that back together now. They put it in this nice little case for us with a cap so it doesn't dry out. This is technology. Boom. Okay? I don't have to dip it in an ink pot. The ink is already inside. Now, we all probably have seen what happens, though, if you take that out and you bust it open. Oh, I know. Oh, I've had that happen here in class before. Somebody was bored. They get their pen out, they take it all apart, and they're playing with it, and they're like, "Ooh, I bet I could take this apart and write with it this way." Oh my God, there's like ink everywhere. I've had it too, where somebody's taken this out and then they've chewed on it, like their whole face is covered in ink. Yeah, I know. 8th graders are crazy people. They are crazy, crazy. Not you, but some 8th graders. All right. I feel like Donald Trump. 8th graders are crazy. Not you, but I imagine some people are good, but not. Yeah. Yeah. Anyway, here we go. So, it says by this process, people identify a need and then they look for ways to meet that need. So, at some point, somebody looked at that feather, dipping it into the ink, and they were like, "Wait a minute. This is crappy and messy. I don't like it. Isn't there something I can make it to make this better?" And yes, eventually somebody figured out how to make it better. Somebody even figured out how to not have to put a cap on it. You know the little clicky pens, right? Clicky pens, somebody figured that out, right? They're like, "Ooh, if I put a spring in here like this and a little clicker on the top, then it'll just come up inside the tube and you won't even need a cap for it." One-piece pen, right? For people like me that tend to lose their caps. Although they did make caps so that they could fit on the other end. That's a good thing, right? All right. So is all technology complicated? Now, if you did what you were supposed to do yesterday in class and read and then do your assignment, which some of you did, and I graded it already, and you can go back in and take a look at your grade and redo it if you want more points. Some of you, I don't know if you all did it or not yet, but you should. But no, technology does not have to be complicated. Is this complicated? No, this pen is not super complicated, okay? So in the reading, they give you an example of a zipper. Zipper's simple. It's actually pretty easy to understand if you take a look at what a zipper is. It's like these teeth on two sides, and then you've got this little glider thing, and as it glides, it joins the little teeth together. And then if you bring the slider down, it unjoins the teeth, so it opens and closes. Now, a few hundred years ago, if one of my favorite shows is Outlander. I actually read the books too, so I don't know if your moms are into that or not, but Outlander takes place, it's set, she travels from the 1900s back to the 1700s, and when she gets back there, they don't have things like zippers. So imagine your clothes. How do you fasten your clothes if you don't have zippers? Buttons.
Yeah.
Lots of buttons sometimes. Sometimes they had to have like if your sleeves, like they had fitted sleeves a lot back then. So you can't have a fitted sleeve and expect to get your arm all the way through it because your hand generally is bigger than like your wrist and stuff. So they would have it so that it would button the whole way up. And it would be button, 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 button. That's why rich ladies always had somebody to help them get dressed. Because like if the back of your dress was just button, 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 all like 50 buttons down here, it would be very difficult for you to do that yourself. You would always need help. That's why, they had people that help them get dressed, you know. But eventually, you know, stretchy fabric came along and zippers were invented. And zippers, you know, not that a zipper is easy, ladies. I know that if you've worn a dress, guys, I'm not talking to you because I can't even think of what, like your jacket zippers. Oh, that's really hard right there, right? But ladies, when we put dresses on, a lot of the times it zippers from here up to here. And you can get it, you're like zipping it up as far as you can up this way, and then you got to reach back. And I mean, you can do it. You can do it by yourself, but it's still a little difficult, right? But you can do it by yourself. So that was definitely technology. It made life easier, at least I would say it definitely for women. But it's not a complex technology. It's inexpensive to make, and it doesn't require electrical energy. So I also put that it was easy to understand as one of the answers, but the answers that I was really looking for when I was looking for, you know, 2 characteristics of a simple technology: inexpensive and requires no electrical energy. Okay, a zipper does not require electricity. All right, pretty simple. There can be complex technology too, though. I mean, a computer, your iPads, telephones. That's pretty complex stuff, you know. It's got circuit boards in it, and it needs battery and all that stuff. So it does require electrical energy. It's often fairly expensive to make, which means then that it's fairly expensive to purchase, right? And it's not always easy for the common person to understand. It requires knowledge of electronics to put it together, to know how it works, and not everybody has that kind of knowledge, okay? Some people do. Some people don't. Computers are a complex device, and it performs very useful functions. Now, we have computers now. I mean, our phones, you know, this big, our phones basically are computers. They can perform pretty much anything that a computer can, but also here's a laptop, right? That's a computer. I can carry this around with me. The first computer was the size of this classroom. So over the years, computers have gotten much, much smaller. And a lot of that is thanks to the processors, which they've figured out, microchips they've made smaller. All the parts that are in that laptop were in the first computers. But instead of being teeny tiny, they were really big. And so the computer itself was big. So computers, while that was an awesome technology that came about, they are still advancing. We are still gaining technology in the computer world. And we are making computers smaller and smaller. I mean, your smartphones, while they can't do exactly everything that a computer can do almost everything a computer can do. I mean, pretty much if I had a keyboard that went with this, which I probably can get, I don't know, but you probably can get a keyboard that plugs into one of these, right, and then type on it. I don't know. I would need like some better glasses to type on a screen like this, though. But it can pretty much do everything that that laptop can do. Right? Last night we were looking for Danny's phone number. We got on Power School, and while it looked a little bit weird on my phone, we found the information we needed right here on my phone. Right? Well, that's what we were trying to do, but we didn't have her number. Okay. But so it goes to show you that even at the high school pool, with my phone, I can look up your information in Power School, okay? Which I never tried it before, and now I know. So all I need now is my phone. I'm not even going to need that iPad in a couple years. Although, yes, I will, because of these, right? Getting older. Although, maybe in a couple years, they will be able to fix my eyes, right? They already have LASIK, and if you have certain things wrong with your eyes, you can get that fixed. I don't qualify right now. Bummer. So what do engineers do? They make our lives easier, pretty much, all right? An engineer, or engineering, is the application of science and mathematics to solve real-life problems. So an engineer is somebody that uses science and mathematics to solve real-life problems. And there's all sorts of different types of engineers, which we're going to look at tomorrow. So please make sure that you guys have your iPads with you tomorrow and that they are charged up, okay? Which means go home and plug them in. Because even though your iPad is a complex technology, it still requires electrical energy, and you need to charge it up. Okay? So we're going to stop here for today because the bell's going to ring very quickly here. Save that note packet. You're going to need it later. And make sure that tomorrow you have your iPads with you. I'm going to talk to you about different types of engineers tomorrow, and you're going to look up some different types of engineers.
Did you do that Spanish information?
Yes, I gave them a note and supposedly they fixed it. All right, any other questions? Maybe that relate to engineering.
Can we not do this, like, finish the rest of it and run over there?
What is that?
Maybe.
Eyes, can't see. Is it the movie sheet?
No, it's not.
Oh, you keep it. I just said keep it. We're going to finish it. Yes, we will finish it. All right, I guess...